Okay, so the next thing that we're going to look at is when we have a function composition, a function in a function. And the chain rule is fairly simple to state, but it's one that we typically need to practice. So that's why I said we're going to spend a couple of days working here. But the way I think of this is if f is the outside function, and I think g is the inside function, it's the derivative of the outside times the derivative of the inside. That's the pattern that we're going to be looking for. And we'll talk about some strategies for how to figure out who the inside function is and who the outside function is. But generally it comes back to your order of operations. But I won't say too much until we actually try this. So I'm going to do this as our proof for the day. This is probably the easiest proof we've done so far. So hopefully you're getting the hang of watching a proof or following it. But I'm going to do it on a different slide. So just to have a nice clear sheet. Okay, so the definition of derivative I'm going to use for this is the one which is the alternative form. Okay, and it's function composition that I'm looking for. So f of g of x minus f of g of c. And it's going to be over g of x minus g of, sorry, whoops. It's going to be over x minus c. So that would be the definition for the composition. And we're going to try to figure out the proof. This one's nice because there's only one step to it that gets you there. So the one thing that we would want to add into this to try to pull this into the two pieces, outside function, inside function, is g of x minus g of c. And to balance it out, I can't just do that without keeping things equal. So basically I just multiplied by 1. There is no change then to the limit. So now the only thing that I'm going to do is rearrange a little bit. And to rearrange, I'm going to be looking for a different limit here. So it'll be the limit as x goes to c of f of g of x minus f of g of c. And I'm going to switch the two denominators. This multiplication here, so the order, that's a legitimate move. We can switch the order. Okay, so at this point, you should recognize one of the pieces now. Hands up if you recognize something. Oh, you're very honest. I thought somebody would at least just lie and stick their hand up. No? Anybody notice anything there? We want to get away from limits, right? One piece now can be removed from all the limit process. Yeah, Connor?
Isn't the second part equals?
No. Well, this part here, this is the definition for g prime of x. This is the alternate definition. So this is the derivative of g of x. Okay. Now, it looks really funny here because these are g of x's and g of c's, but this is the same pattern in this piece, which is the derivative of f evaluated at g of x. So this is the derivative of x if I was to evaluate it at g of x. So those are the same two pieces we were just looking for. So that completes the proof. Okay, so again, in this course I'm not expecting you to do a lot of proofs, but I am expecting you to get a little bit more comfortable, more familiar. Those of you going on to the engineering disciplines, unfortunately your life will be filled with them next year. The rest of you, it depends on how nice your professor is. So anyways, let's try using the chain rule. This was the advice I gave you just a little earlier, was to say, think of it as having an inside and an outside function. That's what we want to try to pick out. So today we're just going to go with the simplest part of it. Okay. So for example, if I had this 3x squared plus 1 all to the 7, does anybody see an outside function there? You could just describe what an outside function would do if you do see it. It doesn't always hit you right away, but does anybody? Danny, sure. Yeah, this is what's happening on the outside here, this power of 7. So just so that, I don't want to put too many x's into this, so I'm just going to say this is what my outside function looks like. you put something into here, into this square, it'll raise it to the 7th exponent. The inside function is 3x squared plus 1. And if I wanted to take the derivative, I only need to think of this piece here in order to get the derivative. So that's going to be 7 times whatever the inside function was to the 6th. So that's 3x squared plus 1. And the derivative of the inside, that's this piece here, is going to be 6x. So together, these pieces make up the derivative for that entire function. Now if you consider your alternative, you'll find this very simple by the end of the block. I know it's kind of strange at the moment, but to give you an idea of the alternative, without chain rule, the only thing you'd be able to do here is expand it, right? Expand it to the 7th term. That could take you quite a while and quite a bit of pen and paper work, which, you know, by the time you collect all your like terms, expand it out, it's just going to take you way longer than the calculus part of it will. So chain rule has its advantages, and there are some situations where we wouldn't be able to do the derivative without chain rule. Okay, so let's try one more together, and then I'll have you do a couple by yourself. Okay, so for this next one here, 3 times x plus 5 to the 2/3. Does anybody see an outside function? Anybody describe what's happening on the outside? Slow down. I can't answer everybody at once. Well, how about x plus 5? Does that look like it's on the outside of this? No. X plus 5 is what we're going to be doing first. So in this situation, you can think about it like this. You put something in to that box, and it will go 3 times that to the 2/3. So the inside function here is x plus 5. And the derivative for the outside piece, I have to look over here. Okay. That'll be 2/3 times 3 using the power rule. So that gets me 2. And I take 1 away, will be negative 1/3. Oops, sorry, I'm not using that. I'm supposed to be using brackets. And the inside piece is x plus 5. Okay. The derivative for the inside piece, that's just here. The derivative is 1. So together, these two pieces make up the entire derivative. Okay? So I'm going to have you try that, talk to your neighbor, and see that you agree about all the pieces. So here's the next two. 1 over x plus 1 and the square root of 3x squared minus x plus 1. So give that a shot, see what your neighbor has to say, and we'll try them together. Okay, so I can see some people have finished the first one, so I'm going to catch up. You can, this would be, we put something in and it'll take its reciprocal. X plus 1 would be the inside function. And that means the derivative for the outside, it's going to be negative 1. Take 1 away is negative 2 using the power rule. And then the inside was x plus 1. So the derivative of the inside is still 1. Okay, so those two pieces together make up the complete derivative. This would be the complete derivative here. Okay. For the last piece, because we like to use the power rule, it's often best if we think about this as the exponent 1/2. Okay? That makes the inside piece 3x squared minus x plus 1. And if I use the power rule, the derivative for this outside function here is going to be 1/2. And it's negative 1/2 for the exponent now that I've taken 1 away. And 3x squared minus x plus 1. Okay. The derivative for the inside piece is 6x minus 1. So this product gives me the complete derivative here. So if you're like 60–70% sure or better that you're on your track, let me just see. Okay, so we're moving pretty good then.
What are
yes.
the boxes for? Like
Well, I didn't want to write, I could write this as the outside is x to the 1/2, but then it gets confusing with all the x's everywhere. So I'm just saying this is the outside one, stick something in that box, that's the inside function goes in there. Okay, so however you'd like to, it's a bit abstract, so however you'd like to represent that. Okay, the next piece here, I'd like you to try this. I'm going to show you how, when you're comfortable and you know you're comfortable, how quickly this can go. So for example, I look at this, and I see the outside function as being what do you think? Someone describe what the outside function does? Cubing it, right? So then what I would do in my head is I would say, okay, so there's the derivative for something which is cubed, and the derivative of the inside is going to be 2x. So if you're comfortable with the chain rule, that's about the speed and efficiency you'll be able to work with. It may not be right now, but hopefully by the time your homework's done today, you can do it with that efficiency. So see how you do then with the next two? Can you do it at that efficiency? That would be great. If not, that's okay. We'll keep practicing a bit.
These two are multiplied together.
Sorry?
These two multiplied together.
Yeah, those are multiplied together in the chain rule.